All right, so we were just looking at the different types of phases, looking at liquids, and we learned about a little bit about pressure and how barometers can read pressure, and you had 760 torr, 760 millimeters of mercury, 1 atm, 101.3 kPa. Those are all the different pressures at standard room temp. And so one of the things that we all have, hopefully, in all buildings, is a manometer. A manometer has like one area that has pressure to another that can be compared to how much pressure is being pushed down, kind of like the barometer, only it's called a manometer. And the manometers we have in our school and hopefully in your home is an actual toilet, where there is part of the toilet that has air in it. There is pressure put on the inner part. This is why there's the flow. So you have this, and you can tell how much pressure is being put or how much is in the atmosphere by looking at the level of the water in the toilet. And as you can see, as there's more pressure, more atmospheric pressure, it pushes down on this side. This would be like the opening part of your bath, the toilet. And the less pressure, the higher it goes. And it compares the pressure of a confined gas to an atmospheric pressure. Again, just like a toilet. All right, we're going to go back to vapor pressure. Remember, vapor pressure was like that evaporation rate, how fast things were able to evaporate. Well, how do we determine it? It is determined by, number one, temperature. The higher temperature, the more molecules will be able to break through that intermolecular force and escape the liquid phase into the gas phase, right? And you can see this here. The second thing is those actual intermolecular forces. So, like nonpolar liquids, like acetone, tend to evaporate more quickly than polar liquids, like water. Liquids that easily evaporate due to low intermolecular forces create a high vapor pressure in a closed container and are considered volatile. So you could think of nail polish as kind of volatile because they tend to, the liquid in the nail polish evaporates really, really fast. All right. So the vapor pressure of a liquid increase with the temperature. The increase in the temperature, more evaporation is happening. So you see vapor pressure curve. Yes, we have one in our reference table, table H, right? So vapor pressure varies from liquid to liquid. You can see all of these have different vapor pressures, and it indicates the strength of the intermolecular force. The quicker it evaporates, the less the force, the weaker the force. The longer it takes to evaporate, or the higher the temperature, that is more forces, stronger forces. So let's look at this. At 40 degrees Celsius, water has a vapor pressure of 50. How do we know? Well, here's 40. I go right here, go over, it's about 50. Okay. While ethyl alcohol has a higher vapor pressure of 145, which would mean that water has the more stronger intermolecular force, which means it's more polar than ethyl alcohol. You want to look at the temperature. The higher the vapor pressure, the weaker the force, weaker their intermolecular force. All right, so boiling point. This comes into effect. What is boiling point? This is the temperature at which vapor pressure equals the external pressure acting on that surface liquid. So we have a thing called normal boiling point. Okay, this is the boiling point of a liquid at standard pressure. Now you can get a different boiling point by doing different things to it, but we'll get into that later. If atmospheric pressure is low, water boils below 100 degrees Celsius. So looking at this, if it is below, if that pressure is below, it will it will be less than 100. All right, that pressure. All right, and like I said, table H, awesome, tells us our lovely little propanone, ethanol, water, and ethanoic acid vapor pressures. Now, I did have you guys do a POGL that includes this, and we did get to see, I believe, propanone, ethanol, and water. All right, so real quick exercises. What is the vapor pressure of ethanol at 90 degrees Celsius? Or 90 degrees, yeah, Celsius. I don't know why there's a line right there. It's probably something else. So let's look at this. Ethanol, 90 degrees, 75, 80, 85, 90. So I follow this line all the way up. I'm going to go until it touches the ethanol line. So be very careful about this, that you actually touch the ethanol line and you don't look at water, or you don't look at ethanoic acid, or you don't even look at propanone. You look at ethanol. And so once I get to that, I can then follow it across and I find it is 150 kPa. But it wants it in torr. So what do I got to do? I got to do my conversion. So 150 kPa goes to 760 torr. That's at standard pressure. And 101.3 is the standard pressure for kPa. You divide this and you should get 1,130 kPa. All right, what is the normal boiling point for propanone? That's what this line is right there. So I'm going to find right here, this is where it is the normal. That's the dotted line, standard pressure. I'm going to follow it down. And yeah, my line kind of got crooked. So it should be about 55 degrees Celsius. Pretty cool. All right, which has stronger intermolecular forces? Propanone or ethanol? And why? Well, looking at this, remember, if as you go up, the one that is lower down has the stronger force. So ethanol, because it takes a higher temperature to boil to overcome those forces. So look at this. The boiling point at normal for propanone is 55, whereas ethanol is up here at 80. Water is all the way up here at 100, where ethanoic acid is even higher at 117, I want to say. So this one has the strongest forces, while this one has the least, or the weaker forces. So if atmospheric pressure is 140 kPa, oh sweet, kPas, at what temperature will water boil? So I got to find 140. If that's 150, 140 should be right here. I'm going to follow the line all the way over to water, and then I'm going to follow all the way down, and it is roughly about 110 degrees Celsius. Okay. All right, so we looked at the vapor diagrams. Now we're going to, vapor curves. Now we're going to look at phase diagrams. So this is these phase diagrams. What the heck is up with this? Well, it helps us to look at equilibrium. It helps us to look at the different phases, boiling point, melting point, all that fun stuff. So equilibrium can exist not only between liquid and vapor phases of a substance, but also between solid and liquid phases and solid and gas phases of a substance. A phase diagram is a graphical way to depict the effects of pressure and temperature on a phase of a substance, any substance. So you're going to look at this. You're supposed to label this solid, liquid, gas. And if this is solid and this is gas, right here, the line between would represent sublimation or deposition, depending on the way you go. Solid to liquid, this would be melting, freezing, depending on the way you go. And again, right here, liquid to gas, it would be vaporization, condensation, depending on which way you're going, up and down. All right, so this is temperature, this is pressure. So you're going to label it something similar to this. solid, liquid, gas. And then you have this point right here. This is called the triple point. That's where all three properties exist at once. And the really cool thing is you can actually see that, well, you can't see it, but this actually occurs on Earth. We can go to it in like a submarine, and that would be underwater at a ridge. That is where the lava is coming up from underneath the crust, and it's hitting the ocean. And the ocean at this point in time has, number one, lots of pressure on it, lots and lots and lots of pressure. And the temperature is actually kind of cold, but you have this hot lava hitting. So you have like a juxtaposition of really, really cold and really, really hot hitting at the same time. So all three phases will happen at the same time. You will get a solid, you will get a liquid, and you will get a gas at the same time. It is super cool. And then you have this critical point, which we will talk about a little bit later, but it's where you can get both liquid and a gas at the same time. All right. So looking at this phase diagram for carbon dioxide real quick at 4 atm, so it's somewhere in between here, and negative 50, well, there's negative 56, so it's got to be over here. So right here, going about here, negative 50. What does carbon dioxide exist as? Well, looking at this, it's got to be a gas. All right. Under normal pressure, what temperature is required to solidify carbon dioxide? Remember, normal is 1 atm. Solidify is going to be right here about negative 78.5. At negative 65, right about here, what is the minimum pressure required to liquefy carbon dioxide? So if I go up, like straight up, it can't happen. It's not even possible. All right, I think there are different questions in your worksheet. Try to do those based on the phase diagram that you're given. If you have any questions, please feel free to ask. And besides that, I hope you guys have a great day.